Hello, everybody. Thank you for sticking out for the last talk of today. We probably all know that different combinations of coexisting aluminum silicate polymorphs, Andalusite, Kyanite, and Sillimanite, have been reported from a number of regional and contact metamorphic terrains, where they have been used as index minerals to understand pressure temperature evolution during metamorphism. The most common interpreted crystallization sequences include Kyanite and Sillimanite formed sequentially before or after low pressure Andalusite crystallization. The sequence Kyanite Andalusite Sillimanite is less common and probably linked to polymetamorphism during unrelated orogenies. This contribution uses cell dissection modeling to explore aluminum silicate polymorph stability in a metapelitic rock from the northern Andes in Colombia, which preserves Andalusite and Kyanite porphyroblasts along with fibrous Sillimanite. The main purpose is to estimate peak PT conditions in the analyzed sample and to understand the characteristics of the association in the evolutive context of a late.
Sorry to interrupt, Carlos. Do you want to swap to presenter mode?
All right, sorry. Let me go again.
You're just not in presenter mode yet. There we go.
Okay. Well, I was then telling you that this contribution uses cell dissection modeling to explore aluminum silicate polymorph stability in a metapelitic rock from the northern Andes in Colombia, which preserves the Andalusite Kyanite porphyroblasts along with fibrous Sillimanite. We also hope to understand the characteristics of the association in the evolutive context of a late Proterozoic to early Paleozoic crystalline core of the northern Andes. I'm going first to show you a brief summary. Excuse me 1 second. Of the regional geology, then I'm going to show you some sample descriptions, followed by modeling, and finally by conclusions. The image on the left shows the regional tectonic framework of the northern Andes, where we see that the evolution of the northern Andes is constrained by the interaction of several plates, including the Caribbean plate, the South American plate, and Central Pacific plates on the west. On the right, I show you an interpretation of the geologic domains of the northern Andes. So interest for us is this central domain and this triangular shaped region that groups most of the northern Andes in Colombia. Those two domains, provinces, have several crystalline cores. One of the most prominent ones is called the Santander Massif, located here, where we can see records of different tectonic episodes starting since the Mesoproterozoic, with ages indicating an orogeny with ranges on ages similar to the Grenvillian orogeny in North America, and ranging to the most recent tectonic events that are related to the Andean orogeny, where we have thermochronological ages and sedimentary sequences indicating the different impulses of this Andean orogeny. But most important for us are these two tectonic episodes. One is, these two tectonic episodes, one is an Ordovician orogeny, and the second is a Jurassic magmatic arc, because we are going to make the interpretations in the light of the presence of these episodes and how these episodes affect the Santander Massif. The Jurassic magmatic arc is wide distributed in the Andes. Here in the northern Andes, we see the distribution of the volcanic and plutonic rocks in Colombia, and the ranges of ages from 150 to 120 million years ago. Although it's not shown here, there is also volcanosedimentary sequences associated, And when we plot this on top of the map, we don't see any difference in location between those volcanosedimentary sequences and the volcanic and plutonic rocks. This is important for the interpretation I'm going to show you later. On the left, we can see a generalized geologic map of the Santander Massif here in the northern part of the Andes. The two units that record the Ordovician orogeny are the Bucaramanga gneiss and the Silgará Schist. The Bucaramanga gneiss also have relics of ages from the Grenvillian type orogeny, but the main metamorphic event is right here in the Ordovician. Also, we see a sedimentary sequence of Devonian in age, which shows low-grade metamorphism. And of course, here also we see the representation of the Jurassic magmatic arc with intrusive and volcanic successions. The characteristics of the massif shows an increasing grade toward the innermost pass of the massif in a northwest axis, crossing here close to this Berlin town. To see some of the rocks we're talking about, we start with the lowest grade ones. This is the Devonian sedimentary sequence with low grade metamorphism. It's a phyllite. We have also here two schists. One is a garnet staurolite schist, and the other is a staurolite kyanite plagioclase schist from the Silgará Schist. Note that we have a regional Sillimanite isograph that marks the boundary between the Silgará Schist and the higher grade unit, the Bucaramanga gneiss. As we increase the grades, we see the appearance of sillimanite, cordierite, and the appearance of abundant leucosomes in the innermost part of the massif. Here we see the cordierite gneiss. Over here, this is a sillimanite schist, and this is a granitic leucosome within a quartz feldspathic gneiss. Some thin section microphotographs to represent some of the associations. In the schist, we see the association garnet kyanite and also staurolite with garnet, although garnet is not shown here in this image. And in the gneiss, we have a cordierite gneiss with fibrolite associated with the cordierite and a sillimanite schist where we see a prismatic sillimanite. There are also a few reported pressure temperature estimations on the two units that range between 400 and 800 degrees C and between 3 and 11 kilobars. Also over here, we have an interpretation of the temperature reached in the low grade unit using Eli crystallinity index. We see that this unit reached temperatures up to 300 degrees C in the boundary between the epizone and the anchizone. Now let's go to some interpretation using petrographic observations and the pseudo-section modeling. I'm going to show you first modeling on two rocks, one from the Bucaramanga gneiss, the high-grade unit, and one from the Silgará Schist. And later I'm going to show you the pseudo-section modeling for the rock with the 3 aluminum silicates. This is from a sample that comes from the migmatitic part of the Bucaramanga gneiss. We have the cordierite fibrolite gneiss. Note that according to petrographic observations and to the stability fields shown in the pseudo section, we make the interpretation that the peak PT conditions were reached in the mel present field of the pseudo sections, but below the cordierite stability field. Because we don't see garnet on this sample, and you see the green line represented here, the appearance of garnet in the association. As cordierite is not stable in this assemblage field, we make the interpretation that cordierite growth because of an overprinting low pressure event that was not related to the initial peak PT conditions. For the Silgará Schist, we have also some modeling. This is the plagioclase kyanite staurolite schist. The assemblage field is probably located here in this narrow temperature range in the subsoleus region of the phase diagram. Note here that the association of kyanite staurolite constrains very well the pressure stabilization for this rock. And this assemblage field is very close to the plagioclase in most zero line, which is contrasting with the abundant presence of plagioclase porphyroblasts on the rock. So our interpretation is that this plagioclase porphyroblasts grew in a later overprinting low pressure metamorphism not related with the Barrovian type metamorphic event. Let's keep in mind those two interpretations. We're going to use them later. Now let's switch to the description of the sample with the 3 aluminum silicate polymorphs. The sample is located on the southern part of the Santander Massif. Note here that the location is close to a regional fibrolite isograph that marks the appearance of this mineral from the garnet staurolite zone. This isograph is not related to the isograph that we see in the northern part of the massif, where we see the transition from kyanite to sillimanite and the boundary between the Silgará Schist and the Buccara manganese. In these polished slabs, we can see some of the characteristics of the sample, where here we have garnet porphyroblasts surrounded by fibrolite, and then we see porphyroblasts of staurolite, kyanite, and andalusite. Some more images showing the characteristics of the association. Andalusite is closely related to kyanite, as noted here and over here. And again, we see the fibrolite growing around garnet porphyroblasts. Note that this sample is as high an aluminum pillite. It plots on the upper part of the AFM triangle. And some of the characteristics of this model for this sample is that garnet is stable in the whole range of PT conditions displayed on the pseudo-section. Note also the wide stability PT range for staurolite, and that we don't see anywhere on the pseudo-section prediction of the 3 aluminum silicates stable together. We can have kyanite plus sillimanite stable at pressures about 7 kilobar, and sillimanite plus andalusite pressures below around 4 kilobars. And andalusite and kyanite are not predicted stable together. Also, we see that staurolite plus one of the aluminum silicates are predicted in a narrow assemblage field. The presence of kyanite and staurolite in the sample attests for equilibration pressures above 7 kilobars. And according to these observations and the petrographic observations have made, we think that kyanite grew during the Barrovian metamorphism related to the Ordovician orogeny, and then we have a growth of andalusite and sillimanite because of a later overprinting low pressure thermal event, similar to the interpretation of the other two samples I showed you before. The most probably tectonic event that could originate this low pressure metamorphism is related to the presence of the magmatic belt in the Andes, and especially here in the northern Andes. This magmatic belt has been related to a low elevation orogeny because of the alignment of igneous rocks with volcanosedimentary sequences. And this low elevation probably originated the low pressure regional metamorphism seen in the Devonian metasedimentary sequences with temperatures up to 300 degrees C. And also in areas close to the large intrusives, we see then contact auroras that when they join regionally, they can form a regional metamorphic overprinting, causing the growth of cordierite, andalusite, sillimanite, and plagioclase. As conclusions, we have make an interpretation of the presence of 3 aluminum silicates on a metapelitic schist from the northern Andes, where you have Sillimanite, Andalusite, and Kyanite together with garnet, staurolite, and other minerals. This interpretation is based on regional geologic observations, where we have identified 2 tectonic episodes, an orogenic Ordovician event and a Jurassic magmatic arc. And together with pseudo-section modeling, we can have a clear indication of a prograde PT path along the Ordovician orogeny and an overprinting low pressure heating event. Thank you.
Thanks very much, Carlos. That was a really interesting talk and some really lovely pictures of those aluminosilicates. There's one question from Renard who says, what is the evidence that sillimanite formed before Andalusite and that it did not crystallize during the first PT loop?
Well, we think that sillimanite grew after Andalusite. And if you allow me to show you this section here, we think that those 2 minerals, fibrolite and Andalusite, grew along this low pressure heating event, first Andalusite and then fibrolite. We have a prismatic sillimanite in some samples, and that probably grew at higher pressures. But the one that we have in this sample and in other samples that is fibrolitic is showing replacing Andalusite and Kyanite. Besides the growth of this fibrolite around garnet crystals.
Thank you. Just one last question before we go into our last coffee break from Stacey, who asks, could the plagioclase rims on the kyanite grains form due to the crystallization of melt?
Could you repeat that?
So could the plagioclase rims on the kyanite grains form due to the crystallization of the melt?
On these rocks, no, because these are schists, and this is rocks that didn't reach the solidus. We have some magmatic microstructures in the inner parts of the massif, where we have those crystallizing melts forming nice microstructures. But these particular samples, no, because you go up here, you see these samples comes from here. We have a garnet staurolite zone, and then we have a fibrolite regional isograph, where we have the association with Andalusite and Kyanite.